Today we're talking about how the Juniper AI-Native Platform uses mutual information to help you understand which network features, such as mobile device type, client OS, or access point, that have the most information for predicting failure or success in your SLE client metrics. Let's start with a definition of mutual information. Mutual information is defined in terms of the entropy between random variables. Mathematically, the equation for mutual information is defined as the entropy of random variable x minus the conditional entropy of x given y. Now, what does this mean? Let me give you an example. Let's say y is one of our random variables that we want to predict and represents the SLE metric time to connect, and it can be one of two possible values, pass or fail. Next, we have another random variable x that represents a network feature that can have a possible value of present or not present. An example of a network feature can be a device type, OS type, time interval, or even a user or an AP. Any possible feature of the network can be represented by the random variable. Next, we'll look at what we mean by entropy. For most people, when they hear the term entropy, they think of the universe and entropy always increasing as the universe tends towards less order and more randomness or uncertainty. So entropy represents the uncertainty of a random variable. And the classic example is a coin toss. If I have a fair coin and I want to flip that coin, the entropy of that random variable is going to be given by the sum of the probability of x, I times the log 2 of the probability of x. And for that fair coin, the probability is that 50% will be heads plus 50% will be tails, and the entropy is going to be equal to 1. The maximum entropy possible. When we have maximum uncertainty, the random variable will have maximum entropy. If we take an example where we don't have a fair coin, we have some hustler out there and he's using a loaded coin. Let's say the probability of heads is 70% and the probability of tails is 30%. Now in this case, your maximum entropy is going to be 0.88. So you can see that as the uncertainty goes down, your entropy will trend towards 0. If you were at 0 entropy, that would mean no uncertainty, and the coin flip would always be heads or tails. Now let's go back and see how mutual information works with our SLE metrics. Graphically, what does this equation look like? Let's say we look at how this circle here represents the entropy of my SLE metric y, and this circle is the entropy of my feature random variable x. So if you look at our equation, the conditional entropy of random variable y given the network feature x is this area here. If I subtract it to what we're looking for, is this middle segment. This represents the mutual information of these two random variables, and it gives you an indication of how well your network feature provides some information about your SLE metric random variable y. If the network feature tells you everything about the SLE metric, then the mutual information is maximum. If it tells you nothing about the SLE metric, then the mutual information between x and y is 0. Now, mutual information tells you how much information a network feature random variable y gives you about the SLE metric time to connect, but it doesn't tell you whether the network feature is better at predicting failure or success of the SLE metric. For that, we need something called the Pearson Correlation. If you look at the picture of the correlation, it tells us a couple of things. One is the amount of correlation with a range from -1 to 1. The other is the sign negative and positive, which is a predictor of pass or fail. So now we have these two things. First is the magnitude indicating how correlated the two random variables are. Second is the sign which indicates failure or success. If the correlation is negative, the network feature is good at predicting failure. If it's positive, it's good at predicting pass. If the Pearson correlation is 0, it means there is no linear correlation between the variables. But there could be mutual information between the two. But the Pearson correlation does not tell us the importance of the network feature, or if there's not enough data to make an inference between the network feature random variable and the SLE metric random variable. That's given back to our graphic of the circles. There may be one case where I have very high entropy for both variables, but there may be another case where I have much smaller entropy on one of those variables. Both of these examples may be highly correlated with a high Pearson's value, but the entropy of mutual information will be much higher in the first case, which means this random variable has much more importance in predicting success or failure of a feature. I hope this gives a little more insight into the AI we created at MIST. And if you look at the MIST dashboard, The result of this process is demonstrated by our virtual assistant.